If you've ever opened a research paper and thought, I want to understand this, but this is dense, then this podcast is for you. Every day, thousands of research papers are published. Most of them are rigorous, insightful, and almost impossible for non-specialists to read comfortably. But the ideas inside them shape medicine, technology, business, and society. Welcome to One Paper Orbit. We are a research paper podcast. Here, we take peer-reviewed research and turn it into clear, structured conversations without adding speculation, without exaggeration, simply making the original work easier to understand.
And we really try to keep things as accessible as possible.
Today, we are discussing a paper authored by Kyati Mittal, Ruchijek Molamani, and Deepshikapande Katari, titled Type 3 Diabetes, Crosstalk Between Differentially Regulated Proteins of Type 2 Diabetes Mellitus and Alzheimer's Disease, published on May 6, 2016 in Scientific Reports.
This discussion is based on a paper published under the Creative Commons Attribution 4.0 license. The original authors retain credit for their work. This podcast provides an adapted explanation for educational purposes, with full citation and license information provided in the description.
Okay, so let's get right into this deep dive. Type 3 diabetes. I have to be honest with you.
Yeah.
When I first saw the title of this paper, my skepticism radar immediately went off.
I can completely understand that.
Right, because it sounds like, I don't know, a marketing term. We have type 1, we have type 2. Calling something type 3 feels almost like a sequel to a movie franchise that's just running out of ideas.
Yeah, like it's just trying to grab your attention.
Exactly. But the implication here is massive. It implies that Alzheimer's disease, which, everyone understands is a memory disorder, a brain issue, this terrible neurological tragedy, is actually a metabolic disease.
Right.
It suggests Alzheimer's is effectively diabetes of the brain. So is this just a catchy headline, or is this a legitimate medical classification?
It is a very legitimate and honestly a very frightening classification. It's definitely not just a headline designed to sell magazines or get clicks.
Okay.
The authors of this paper, Mittal, Mani, and Katare, are diving into a concept that has been gaining some really serious traction in neuroendocrinology over the last decade. They aren't just saying Alzheimer's is, like diabetes.
Not a metaphor, then.
No, not a metaphor at all. They are presenting hard evidence that a significant subset of Alzheimer's cases are the direct physiological progression of type 2 diabetes.
So we aren't just saying sugar is bad for your brain.
No, it is a specific neuroendocrine disorder. They use the term type 3 diabetes, or T3D, to describe what happens when the exact same insulin resistance that destroys your body's ability to process sugar starts destroying your brain's ability to process memory.
Wow.
Yeah. It is the bridge where the metabolic failure literally becomes a cognitive failure.
That is a massive paradigm shift.
Yeah.
I think most people view these as two completely distinct pillars of aging.
Oh, absolutely.
Like, you might get diabetes if you have a poor diet, and you might get Alzheimer's if you have bad luck or bad genetics. But we don't usually think of the donut I'm eating as directly dissolving my memories.
And that is exactly the crosstalk this paper investigates. That's our mission for this deep dive today. We really need to move beyond the vague idea that sugar is bad for you and actually understand the specific molecular mechanics.
The nuts and bolts of it.
Exactly. The authors are looking at what they call differentially regulated proteins. They are essentially tracking the actual conversation happening inside your cells that says, okay, the pancreas is failing, let's shut down the brain.
Protein conversations. I like that. It makes it sound active.
Yeah, very active.
Before we get into the complex biochemistry, and I know we have some heavy lifting to do there, we need to set the stakes for you all listening. Why are we linking these two specifically right now? Is this a completely new phenomenon?
Well, the phenomenon itself isn't necessarily new, but the sheer scale is. The paper opens with what I kind of call the rising tide argument. We are looking at an absolute explosion of type 2 diabetes cases globally.
Right. It's everywhere.
The authors cite projections that we could hit 592 million cases by 2035.
592 million. That's nearly 10% of the global population.
Correct. It's a pandemic in its own right. But here is the statistic from the literature that really anchors this whole paper. Patients with type 2 diabetes have almost double the risk of developing Alzheimer's disease compared to healthy individuals. Yes, almost double.
That's not a rounding error. That's a coin flip.
Yeah.
If you have diabetes, you have essentially doubled your odds of losing your mind.
Exactly. And the distinction here really matters. They note that the risk is significantly higher for those with full-blown type 2 diabetes compared to those who just have, say, mild insulin resistance but haven't progressed yet.
Okay, so the worse the diabetes, the higher the risk.
Yes, which implies that the progression of the metabolic disease tracks perfectly with the progression toward the neurological disease. T3D isn't just a label, it's an explanation for a massive chunk of the global Alzheimer's burden.
Okay, statistical correlation is one thing. We can find correlations everywhere, right? Ice cream sales correlate with shark attacks, but ice cream doesn't cause sharks to bite you.
Right, the classic causation fallacy.
For this to actually be type 3 diabetes, there has to be a shared pathology. There has to be physical evidence. What does the paper point to?
They point to the absolute smoking gun of Alzheimer's amyloid beta.
Right, the sticky plaque. Anyone who has read anything about Alzheimer's knows about amyloid plaques. They gum up the neurons, block signals, kill the cells.
Yeah.
It's the hallmark of the disease.
It is. But here is the twist that usually shocks people. The paper notes that these amyloid beta deposits are not exclusive to the brain.
Wait, what's that?
In patients with this progression, we actually find amyloid deposits in the pancreas.
The same brain gunk is showing up in the pancreas.
Yes. And conversely, we see hallmarks of pancreatic failure, specifically issues with insulin signaling appearing right there in the brain.
That's wild.
The authors argue that this suggests a systemic failure. For decades, we have been treating them as two entirely separate organs. The pancreas manages sugar, the brain manages thought.
Right.
But if you have the exact same toxic protein accumulating in both, and the same signaling pathways breaking down in both, it heavily suggests they are victims of the same crime.
That is a powerful image. It's like finding the same arsonist signature at two completely different fires. You just stop thinking it's a coincidence.
Precisely. And the fuel for that fire is insulin.
Which brings us to the next big point. We need to talk about insulin. And I'm going to play the everyman here for a second, because I grew up thinking insulin was strictly the blood sugar hormone.
Most people do.
You eat a meal, blood sugar goes up, the pancreas squirts out insulin, your muscles eat the sugar. End of story. Why is insulin even talking to the brain? I thought the brain was protected behind the blood-brain barrier.
That is probably the most common misconception, and the authors address it right in the introduction. They state clearly that insulin signaling pathways are conserved in various tissues.
Conserved.
In evolutionary biology, conserved means it's so fundamental, so important, that evolution kept it working the exact same way across different biological systems. The brain is not an island.
But the blood-brain barrier is real. It's a fortress. It's supposed to keep things out.
It is a fortress, yes, but insulin has a VIP pass.
Really?
The paper explains that insulin reaches the brain via cerebrospinal fluid, but more importantly, it is actively transported across the blood-brain barrier via specific receptor-mediated transport. The brain literally invites insulin in. It pulls it from the blood.
Okay, if the brain is actively inviting insulin in, it must have a job for it. It's not there to lower blood sugar. I mean, my thoughts don't have calories.
Well, your thoughts do burn energy. A lot of it.
Fair point.
The brain is an absolute energy hog, and that is exactly what insulin does there. The paper details that insulin receptors are highly concentrated in the hippocampal region and the cerebral cortex.
The hippocampus, that's the memory center.
Exactly. It's the seat of learning and memory. The authors explain that insulin stimulates the translocation of a protein called GLUT4 to the neuronal membrane.
Okay, let's break that down for the listener. Translocation of GLUT4. What does that actually look like in plain English?
Imagine a neuron is a house. It needs fuel glucose to keep the lights on and the memories forming, but the doors are locked. GLUT4 is the door.
Okay, I'm with you.
Normally, GLUT4 is just sitting inside the house, in the hallway, completely useless. When insulin arrives, it rings the doorbell. That signal tells the neuron to move the GLUT4 door to the outside wall and open it up.
So without insulin ringing the bell, the door just stays inside.
Correct. Without insulin signaling, the door stays shut. The glucose simply cannot get in, and the neuron starves.
So brain diabetes is literally a starving brain. Even if your blood is absolutely full of sugar, the neurons are starving to death because the insulin key isn't opening the door.
That is the essence of it. The paper calls this the pancreas-brain mirror. They note that beta cells in the pancreas, the ones that make insulin and neurons in the brain, respond to glucose stimuli in a very similar fashion.
How similar?
They use the same electrical mechanism. It's the depolarization of ATP-sensitive potassium channels. They use that to sense energy. Biologically speaking, they are cousins.
Wow. There was one other detail in this section that really threw me, though. The paper mentions that the brain might not just be importing insulin, it might be, well, making it.
Yes, this is a bit controversial, but it's an increasingly supported idea in the field. The authors cite studies showing that insulin has actually been found stored in synaptic vesicles at nerve endings in rat brains.
So it's right there at the synapse.
Yes, and it is released when the nerves fire.
So the brain basically has its own insulin factory.
It definitely appears so. This implies the brain has a local economy of insulin, totally independent of the pancreas.
That raises the stakes even higher. If type 3 diabetes is a failure of this local factory, then taking insulin shots for your body might not even fix the problem in your head.
Exactly. It strongly suggests that the brain can become insulin resistant independently, or that the breakdown in the brain is a specific, localized failure of this machinery.
That's terrifying.
It is, which is why type 3 is such a necessary classification. It forces us to look at the brain's specific metabolic needs, which might be entirely different from the rest of the body.
All right, so we've established the crime scene. We have a brain that is starving and full of plaque. We have a suspect insulin signaling. But how do they actually prove it?
That takes us to the methodology.
Right, this brings us to what I call digital biology. Because this paper didn't involve taking blood samples from patients in a clinic, did it?
No, not at all. And this is really where modern biological research is shifting. They use network-based strategies.
Which honestly sounds like something a tech startup does.
It's essentially big data for biology. Instead of looking at one protein in a test tube for 5 years, they looked at the entire system at once. They performed extensive literature mining to identify proteins that are differentially regulated in both diseases.
Differentially regulated. Just to clarify, that basically means proteins that are behaving badly.
Yes. Proteins that are either upregulated, meaning there's way too much of them, or downregulated, meaning they are missing or suppressed in patients who have both type 2 diabetes and Alzheimer's.
Got it.
So they created a hit list of about 70 query proteins.
Okay, so they have a list of suspects, 70 proteins acting weird in both diseases. Then what do they do with that?
Then they cross-reference this list against massive biological databases, systems like HPRD, BioGrid, and String.
What are those exactly?
Think of these as social networks for molecules. They literally tell you who interacts with whom. Does protein A talk to protein B? Does it activate it? Does it destroy it?
Oh, I see. And this generated the image in the paper figure 1. I remember looking at it, and it just looks like a giant hairball.
We literally call them hairball graphs in systems biology.
Do you really?
We do.
It's just a mess of balls and sticks. The balls are proteins, the sticks are the interactions. They started with 70 proteins and ended up with a network of 957 interacting partners.
It perfectly illustrates the complexity we're dealing with. You pull one string diabetes and 957 other things move. But they didn't just stop at making a pretty picture, they ran the math on it.
Right.
They calculated the statistical probability of these pathways overlapping by random chance.
And this is the number I really want to highlight for you all. It was 2.7 E79.
It is a number so small it is genuinely hard to comprehend.
For the listener, that is a decimal point, then 78 zeros, and then a 2.
To put that in perspective, in science, we usually get excited about a p-value of 0.05. That means there is a 5% chance it's a fluke.
Right, the standard threshold.
2.7 E79 means it is statistically impossible that this is a coincidence. The insulin signaling pathway is not just involved in Alzheimer's, it is completely central to it.
It's the superhighway connecting the two cities.
Precisely. They also found other shared superhighways apoptosis, which is cell death, MAPK signaling, immune responses, but the insulin pathway was the absolute strongest link.
Okay, so the link is real, the math proves it, but a network map doesn't really tell you the story. It's like looking at a map of roads. It doesn't tell you why the traffic jam happened in the first place.
Right, you need a mechanism.
And the authors had to propose one. They actually came up with 7 routes, or hypotheses.
7 potential narratives of destruction, basically.
And they chose a favorite. Route I. Let's deep dive into Route I, because this is the core hypothesis of the paper.
Route I is the closest and most appropriate explanation according to their network analysis, and it introduces our main character IDE.
IDE, insulin degrading enzyme.
Names in biology are usually very functional. This enzyme degrades insulin.
Which seems completely counterintuitive to me. We just spent 10 minutes talking about how the brain needs insulin to survive.
Oh, yeah.
Why does the body have a dedicated enzyme just to destroy it?
Because in biology, signal termination is just as important as signal activation.
How so?
Imagine if your doorbell rang and then just never stopped ringing. You wouldn't be able to hear the next visitor. The cell needs to clear the insulin away so it can reset and listen for the next sugar spike. IDE is the janitor. It cleans up the old insulin.
Okay, so in a healthy person, I eat, Insulin spikes, cells open, and then IDE comes in to sweep up the confetti.
Exactly. But in type 2 diabetes, specifically in the early to mid stages, you often have hyperinsulinemia.
Which means high insulin.
Yes. Your body is resistant to insulin, so your pancreas screams louder. It pumps out massive amounts of insulin to try to force those doors open.
So the janitor IDE is suddenly totally overwhelmed. There is trash everywhere.
And the body responds by upregulating IDE. It hires more janitors, you have a massive flood of insulin, and a subsequent flood of insulin-degrading enzyme trying to cope with it.
Okay, so we have a lot of insulin and a lot of IDE. Why is this bad for the brain?
This is the double-edged sword. The paper explains it beautifully. Edge number 1 is brain starvation. Because IDE levels are so high and so active trying to manage the systemic flood in the body, they start degrading insulin too aggressively in the brain.
Oh, wow.
In the brain, this overactive degradation means the insulin signal is cut short.
So the janitor's throwing away the mail before you've even had a chance to read it.
Perfectly put. The insulin doesn't have time to dock with the neuron and open the GLUT4 door before IDE just chops it up. So despite having high insulin in the body, the brain experiences a functional deficiency.
That is terrifyingly ironic. You have too much, so you starve.
But edge number 2 is even worse. It's the plaque problem. You see, IDE is a moonlighting employee. It doesn't just degrade insulin. It is also the primary enzyme responsible for degrading amyloid beta.
Ah, I see the collision coming right now.
It's a direct competition. IDE has a much higher affinity for insulin. So when you have a flood of insulin from diabetes, IDE basically ignores the amyloid beta to focus on the insulin.
So the janitor is busy in the kitchen cleaning up the massive sugar spill, and meanwhile, toxic waste is just piling up in the living room.
And that toxic waste is the Alzheimer's plaque. The paper states that the diversion of IDE to insulin leads directly to the accumulation of amyloid beta. So root I gives us a mechanical, physical explanation for why diabetics get plaques. Their clearing mechanism is simply distracted.
It's a resource management failure. The body just can't handle both crises at once.
Correct. And eventually, the IDE system itself might fail or become completely dysregulated. That leads to the worst of both worlds. No insulin signaling, which causes starvation, and no plaque clearance, which causes toxicity.
That is the core hypothesis. But root I doesn't stop at IDE, does it? It traces the dominoes that fall after the janitor fails.
It goes much deeper.
This brings us to Section 5, the downstream chaos. I really want to walk through this chain reaction for you all because it connects a lot of buzzwords people hear about health, inflammation, oxidation, genetics.
It really does tie it all together. So domino 1 was the IDE dysfunction. Domino 2 is IGF-1, or insulin-like growth factor 1. The paper indicates that high IDE activity downregulates IGF-1.
Why do we care about IGF-1? What does it do?
Think of IGF-1 as the contractor. Its job is neurogenesis and synaptic plasticity. It repairs damaged neurons and builds new connections. When IDE suppresses IGF-1, the repair crew goes on strike.
So the brain stops healing itself.
Exactly.
Okay, domino 3.
When the repair crew is suppressed, it triggers a sharp rise in IL-1B, which is interleukin-1 beta.
Interleukin, that sounds like the immune system.
It is. IL-1B is a pro-inflammatory cytokine. It's the fire alarm. When this spikes, it causes massive neuroinflammation and oxidative stress.
Let me get this straight. So now we have a starving brain, no repair crew to fix anything, and the building is literally on fire.
And the fire spreads to your genetics. IL-1B interacts with a protein called A2M, or alpha-2 macroglobulin, which then directly impacts APOE.
APOE, I know that one. That is the famous Alzheimer's gene. If you have the APOE4 variant, your risk absolutely skyrockets.
Exactly. And here we see APOE not just as some static genetic risk you're born with, but as an active cog in this broken machine.
How does it break?
The dysregulated APOE fails to manage lipid transport effectively, which finally leads to the processing of APP amyloid precursor protein into the deadly plaque.
It connects the dots perfectly. Let's recap that. Insulin resistance leads to a distracted janitor, IDE. That leads to no repairs from IGF-1, which leads to inflammation from IL-1B, which triggers the genetic vulnerability of APOE, which finally creates the plaque.
It's a direct line of sight from the sugar in your blood to the death of your neurons.
It makes it feel so mechanical, like a car engine just seizing up because it ran out of oil.
That's a great analogy.
But the authors didn't just stop at root 1. They mapped out roots 2 to 7th as well. We can't cover every single protein today, but I think the ensemble cast is important because it shows this isn't just about insulin. It drags in other systems.
Absolutely. Root on is definitely the favorite, but the others are likely happening in parallel. It's not either or. Take route 2, for example. I tend to call this the suicide route.
Sure.
Biology can be grim. It involves a protein named BA.
Please tell me that stands for something and isn't just a moral judgment on the protein.
It stands for BCL2-associated agonist of cell death, but it definitely lives up to the name.
I bet.
In a healthy cell, insulin signaling keeps a protein called AKT active. Think of AKT as a guard that holds BA down and keeps it quiet.
And when insulin resistance hits?
AKT goes to sleep. The guard is off duty, BAD is unleashed. And when BAD is loose, it actively initiates apoptosis. It goes straight to the mitochondria, the power plants of the cell, and punches holes in them.
So the cell just commits suicide.
Yes. This route shows that neurons might not just be dying because they get smothered by the plaque gunk. They might be actively killing themselves because the stay-alive signal from insulin has vanished.
That is profound. It's not murder by plaque. It's programmed obsolescence triggered by silence. What about route V? That one caught my eye when I was reading because it specifically mentioned fat.
Right, the fat metabolism route. This involves PPRG and RB, which is retinoblastoma protein.
PPRG, wait, that's the target of some diabetes drugs, isn't it?
It is. Thiazolidinediones target PPREG. This route shows that when insulin resistance disrupts lipid or fat metabolism, it affects the MAPK pathway.
And what does that do?
This eventually leads to the aggregation of alpha-synuclein.
Alpha-synuclein, wait, isn't that the Parkinson's protein?
It is, and this is a fascinating crosstalk within the crosstalk. This route suggests that the metabolic breakdown doesn't just lead to Alzheimer's amyloid, it can also lead to Parkinson's alpha-synuclein.
Wow.
It implies a shared metabolic route for multiple neurodegenerative diseases.
So if you break the energy system, you don't even get to choose which brain disease you get. You might just get a mix of them.
Exactly, a spectrum of neurodegeneration.
Yeah.
And finally, look at routes 6 and 7. They bring in leptin.
The satiety hormone, the one that tells your brain you're full.
Yes. These routes show that leptin receptors interface directly with the insulin signaling. It connects obesity, the actual physical state of carrying excess adipose tissue, directly to the molecular production of amyloid.
That's a huge link.
It explains why obesity is an independent risk factor for Alzheimer's. It's not just about high blood pressure or bad circulation. It's about leptin signaling physically crashing into the insulin pathway.
It's overwhelming. It really feels like every single system, sugar, fat, hunger, inflammation, immunity, is completely conspiring against the brain once that first domino of insulin resistance falls.
That is the reality of a biological network. We like to think of diseases as linear. Cause A leads to effect B. But biology is a web. You pull one thread and the whole web vibrates.
Which brings us to the so what portion of our deep dive, implications for treatment. If the web is this tangled, how do we possibly fix it? The authors seem to argue that this sheer complexity is exactly why we haven't cured Alzheimer's yet.
Correct. They address the incurable problem head-on. Think about how we usually develop drugs in modern medicine. We look for a magic bullet, we find one bad protein, and we make a drug to block it.
Right, like taking an antibiotic for a specific bacterial infection.
Exactly. But T3D involves a network failure. We saw 957 interactions in that hairball graph. You cannot fix a 957-part failure with one single wrench.
It makes sense.
The authors strongly argue that targeting amyloid beta alone, which, by the way, has been the main strategy for pharmaceutical companies for 20 years, is simply doomed to fail.
Because you're mopping up the floor while the pipe is still actively bursting?
Exactly. Even if you clear the plaque completely, the IDE is still dysregulated, the inflammation is still raging, the neurons are still committing suicide via BAD, the network is still broken. The authors propose that we need multi-target drugs.
Polypharmacology.
Yes, we need combinations of drugs, or what we sometimes call dirty drugs, that hit multiple targets at the exact same time.
And based on their specific analysis, where should we aim? They constructed this whole map. Where is the X that marks the spot?
They point back to route I. They created a hit list of 5 key proteins, IDE, IGF-1R, IL-1B, A2M, and APOE.
But if they had to pick a captain of that hit list, the main target,
IDE, the insulin-degrading enzyme.
the janitor.
Since the entire cascade starts with the dysregulation of IDE, they argue it is the most logical upstream target. If we can develop an IDE inhibitor, or actually, better yet, an IDE modulator, we might be able to stop the dominoes from falling in the first place.
A modulator, why not just an inhibitor?
Because remember, we don't want to stop IDE completely. We still need it to clean up. We just need to stop it from over-degrading insulin while simultaneously encouraging it to clean up the plaque.
That sounds like a tough needle to thread.
It's a very delicate balance. We essentially need to help the janitor prioritize its tasks.
That sounds incredibly difficult to engineer pharmaceutically.
It is incredibly difficult, but at least we know what we are trying to engineer now. The paper also mentions that anti-APOE antibodies are in clinical trials, which is promising. But therapies targeting IGF-1R have really struggled in the past because IGF-1 does so many different things in the body. You risk massive side effects.
It's not easy, but at least this paper provides a map. Instead of shooting in the dark, we have actual coordinates.
Exactly. It shifts the entire focus of the field from cleaning up the damage to restoring the metabolism.
So let's bring this home for you all. The real aha moment for me in this deep dive is that type 2 diabetes isn't just about managing your blood sugar to save your feet or your eyes or your kidneys. It is literally about saving your mind.
Absolutely.
It is a signaling breakdown that starves the brain, and through that IDE enzyme, allows plaque to build up.
It redefines the stakes entirely. Type 3 diabetes is a useful label because it forces us to look at the systemic nature of the disease. It destroys the old silo between neurology and endocrinology.
They aren't separate anymore.
Right. The brain is an endocrine organ. It responds to hormones. It needs to be treated as such.
I want to leave our listeners with a final provocative thought, something that circles back to that brain factory idea we touched on earlier.
The local insulin synthesis.
Yes. If the brain makes its own insulin, and if type 3 diabetes is partially a failure of that specific local production, are we treating diabetes completely wrong?
It's a valid question.
We give people insulin shots in the stomach, we give them metformin to lower blood sugar in the body, but if the brain has a separate walled-off economy, does that medicine even reach the problem?
That is the billion-dollar question in neuropharmacology right now. The blood-brain barrier might actually be preventing our best systemic treatments from effectively fixing the brain's metabolic crisis.
So we might be fixing the body perfectly while the brain continues to rot.
It is a very distinct possibility. This research suggests we might need delivery methods that specifically target the brain. Intranasal insulin, for example, is being researched right now for this exact reason.
Sniffing insulin to save your memory.
Yes. It suggests that just lowering blood sugar might not be nearly enough to stop Alzheimer's if the brain's local insulin factory is broken. We might need to treat the brain as a patient entirely separate from the body.
That is a fascinating, if somewhat terrifying, frontier. It certainly makes you look at every sugar spike a little differently. It's not just about calories anymore. It's about cognitive decline.
It is. But knowledge is power. Understanding the mechanism is always the first step to fixing it.
This paper is published under a Creative Commons Attribution 4.0 license, and full credit is provided in the episode description. Thank you for listening to One Paper Orbit Out, our research paper podcast. Our goal is to make peer-reviewed research accessible to everyone. If this episode was helpful, please share your thoughts and let us know which papers you'd like us to explore next. Thank you.